Check it out now, y'all.
nanoHUB-U, online instruction.
All right, in this problem we are asked to calculate the ballistic conductance of a block of silicon, and this silicon has its temperatures at either end maintained at 100 Kelvin on one side and 50 Kelvin on the other. We are told that we can use Debye dispersion relations for the acoustic modes, and there are two of those. There's really three total, but if we look at the dispersion relation, we have a longitudinal branch, and then we have a lower velocity transverse branch, and there's two of those. We also are told that there's an optical branch, and in this case there would be three of them, but they have zero group velocity, and so they will not contribute to transport in this case, so we will ignore those right from the start. The way that we define the heat flux, we have a net heat flux that's in watts per meter squared in this three-dimensional problem. And what we do is we sum over the branches and integrate from 0 to infinity, and we have a little bit of an odd way to put this. We have 1/2 times group velocity over 2, and the reason we did it that way, if you'll recall from the lectures, is that group velocity over 2 is an average velocity in the direction of interest. We multiply that by our density of states, which is the 3D density of states in this case, and then we have our energy, the energy of our carrier, h bar omega. We have a transmission function, which, because this is ballistic, we're going to say that equals 1 in this case, and then the whole process is driven by the difference in distribution functions between the left and the right side. And we integrate all of that over frequency, so you can look at how that comes out. Now, the density of states is really the only thing that we have to fix here. Everything else should be fairly well known, and because we have Debye dispersion, we'll just plug that in right away. For a three-dimensional material, that's going to be omega squared over 2 pi squared times the group velocity cubed, and that would be for frequencies less than the Debye frequency, which we're going to have to calculate, and then it's 0 for frequencies greater than the Debye frequency. So we really need to now calculate what that Debye frequency is, and so I'll kind of start with a step behind that with the Debye cutoff wave vector. So that's going to be six pi squared times the unit cell density to the 1/3. This is again a three-dimensional material, and this is a subtlety that I wanted to point out through this example, is that silicon has 2 atoms per unit cell. Therefore, we have that the unit cell density will equal the number given in the problem was 5 times 10 to the 22 atoms per cubic centimeter. So the unit cell density will be half of that. So this is 2.5 times 10 to the 22 cells per cubic centimeter, which is in the problem statement is listed as CC. Okay, so then we find from this just plugging that unit cell density into the expression for the Debye cutoff wave vector, we find that KD equals 1.13 times 10 to the 10th, and this will be, we'll express that in a per meter, so we did some unit conversion. And then from that we have to calculate the cutoff frequency, and so we'll have a couple of different ones. So omega d, the Debye cutoff frequency, equals the group velocity times the cutoff wave vector, and so this will be 8.17 times 10 to the 13th radians per second. That's for the LA mode, the longitudinal acoustic mode, and it'll be something less for the transverse modes. There are two of those. And so we go back and we substitute all of these things back into the original expression for heat flux. So we find that JQ net will equal the integral from 0 to the Debye cutoff frequency for the LA mode, and then we can go back and substitute all the values that we did before. I won't write them out here. And we do the same thing for the TA modes, but we're going to put a factor of 2 in front because we have degeneracy. We have 2 transverse modes. And when we substitute values for that, and we evaluate the integrals, we do that numerically, we find that the net heat flux for this ballistic problem will equal 1.85 times 10 to the 10th watts per meter squared. And those of you who are familiar with heat transfer know that that's a huge number. And you might say, well, is that even possible? And really the answer to that is no. It would be such a high heat flux, it would be hard to find something to generate that level of heat flux. But you could, I suppose, if you went to some exotic extremes. But the broader point here is that we've assumed that the transmission function is 1, when in fact what we'll find in next week's studies is that the transmission function for a real material like silicon will be much, 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 much less than 1, and that's what will moderate the value of this heat flux. All right, that's it for this problem. All right, we're solving problem 4.2, and in this problem we're asked essentially to calculate the frequency where the conductance is maximum. This is for a single phonon branch using aluminum as an example material in 3 dimensions. And also we want to then calculate the number of modes for that particular frequency at which the conductance is the maximum. So we start out with the picture here, just a block of aluminum. We have a 1 by 1 centimeter cross section that's shown here. I'll cross hatch it there. And we are going to assume that we have Debye dispersion. So this is we're interested in phonons here. Of course, for aluminum, there's also a significant electronic component that we're not covering in this problem. But we're going to use the Debye approximation. So if we draw our approximated dispersion, it'll look something like this, where the slope of this line gives us our group velocity, and that group velocity was given to be 3,400 meters per second. And so what we want to do is use the Debye approximation essentially as our approximation for the density of states, which we'll need. But first, we want to answer the part of the question that says, what's the maximum frequency, or the frequency at which the conductance is maximum? And from the lecture notes, we found that for a 3D material, we had that chi for the peak is equal to 3.83, and so that's h bar omega over kBt. And in this problem, we were given that the temperature is 300 Kelvin, and so that means that the frequency at peak conductance will end up being, if we just do a simple calculation of this, plug in the numbers, 1.5 times 10 to the 14th radians per second. And so that's one part of the problem. Now we want to calculate the number of modes. And remember, this is sort of the number of half wavelengths that would fit into a cross-section of the material. In this case, we have a 1 by 1 centimeter cross-section that we'll use in a moment. We had a general expression for 3 dimensions. The number of modes for a given frequency equals the cross-sectional area times omega squared over 4 pi Vg squared. So this comes from really the product, those terms there come from the product of the average velocity in the direction of interest and the density of states. So the density of states here, we've used the Debye approximation for density of states. And we know from the problem statement that the area equals 0.01 meters squared. And again, the group velocity was given above. We then plug in our value for the frequency at peak conductance, as well as the area and the group velocity. And we find that the number of modes is 1.56 times 10 to the 18th. A very, very big number. That's why when we later talk about the quantum of thermal conductance, that's a very small number, but when it's multiplied by a large number of modes, we can have the types of thermal conductances that we see in real life. That's it for this problem.
So this problem number 4.3. This problem is about using a 1D atomic chain to experimentally measure the quantum of conductance. So first, let me just write down the expression for the conductance integral. So GQ is given by KB square T by 2 pi h bar times the integral from 0 to infinity of m of chi f p e naught square chi square e power chi. So this is the integral that was used to calculate the quantum of conductance. Basically, when m of chi or m of omega is 1 for all frequencies, then we get the quantum of conductance. Then this integral basically turns out to be pi squared by 3, and we get the quantum of conductance. Now in the present problem of a 1D chain, so this is the dispersion relation of a monoatomic 1D chain, and shown here is the number of modes as a function of frequency. So frequency is on the y-axis and number of modes is on the x-axis. So basically, since there are no states beyond the maximum phonon frequency, which is here, the density of states is 0 beyond this, and hence the number of modes, which is basically a product of group velocity and the density of states, is also 0 beyond the maximum frequency. So the number of modes is 1 till the maximum frequency, and then it drops off to 0 for any frequencies higher than that. So correspondingly, in this integral here, the upper limit of the integral is only going to be till omega max, where omega max is basically this frequency, the maximum frequency here. and until omega max, the number of modes is going to be 1. So this is going to be FB naught square chi square e power chi d chi. Now, and so it's not omega max exactly, since we are talking about the normalized frequency. It's h bar omega max by kBt. I'm sorry. So this should be h bar omega max by kBt and not omega max as such. So we basically want the value of this integral to be within 90% of to be greater than 90% of pi square by 3. So we basically need to choose this upper limit accordingly. Now if you actually look at a plot of this function here, chi square e power chi fb naught square, the plot looks something like this. So you can see that it's a decaying function. Now the idea is that the total area under this curve, if you consider chi going till infinity, is pi square by 3. But even if you truncate this at a value of around 4.7 or somewhere over here, say this is 4.7, the area beyond that is less than 10% of pi square by 3. So basically this portion over here contributes to 90% of the integral. So if you so basically this upper limit over here should be greater than or equal to 4.7 if we want to measure a value within 90% of the quantum of conductance. So h bar omega max by kBt should be equal to 4.7. And omega max is for a monatomic 1D chain is given by 2 root g by m, where g is the spring constant and m is the atomic mass. So this goes back to chapter 1 of this course. So and if we calculate this by plugging in the values that were given in the problem, this omega max comes out to be 4.63 into 10 power 13 radians per second. And for this omega max, if we correspondingly calculate the temperature comes out to be approximately 75 Kelvin. So basically we need to make sure in our experiment that the temperature should be less than or equal to 75 Kelvin if we want to obtain a value that is greater than or equal to 90% of the quantum of conductance. And shown here is a plot of G by the quantum of conductance as a function of temperature. So basically at very low temperatures this ratio is 1, indicating that we'll get a value that is very close to the quantum of conductance, and then it drops off for high temperatures. So basically this is the temperature that we found out in this problem. The temperature corresponding to the ratio being 0.9, basically 90% of the quantum of conductance. So this is approximately 75 Kelvin, and that is what we found out. So any temperatures higher than that, we would be too far off from the quantum of conductance. That's what it says. And thank you.
Hi. In the fourth problem of the fourth homework, I'm going to discuss the effects of the phonon dispersion and the dimension of the device on the spectral thermal conductance of the system. The dimension of the device, represented by D, can be 1, 2 or 3, corresponding to 1 dimension, 2 dimension and 3 dimensional device, whereas dispersion will be varied by varying the exponent in the dispersion relation. So here n is the exponent of the dispersion relation, and n can vary from n equals to 1 to n equals to 2. N equals to 1 is the linear dispersion, which corresponds to a Debye-like dispersion, and n equals to 2, if you remember, is something similar to what is observed for the ZA mode in graphene. So this problem has 3 parts. In the first part, we will derive analytical correlations for the number of modes m of omega. and we'll see how m of omega correlates with d and n. Okay. In the second part of the problem, I'm going to use the Mathematica CDF tool to plot the chi raised to alpha moments of the normalized spectral conductance, and we will observe some peaking behavior of this normalized spectral conductance as a function of alpha. Now alpha, as we will see from the first part of the problem, will be a function of d and n. And in the third part of the problem, I'm going to take the case of graphene, and we are going to analyze the La, Ta and the Za modes for the spectral thermal conductance. So going to the first part of the problem, the first part of the problem asks us to obtain the scaling relation between the number of modes, which is m of omega, and the non-dimensional energy represented by chi. So chi here is h bar omega upon kb t, where omega is the frequency and t is the temperature, and this is under the assumption that the dispersion is given by omega scales as k raised to n. Omega is the frequency, k is the wave vector, n is the exponent, and d is the dimension of the system. Okay. Now, from your lectures you will recall that the number of modes in the system scales as the product of the group velocity and the density of states. But we also know that the density of states scales as k raised to d minus 1 upon the group velocity. Here again k is the wave vector, Vg is the group velocity. So if I plug in these values here, I'll see that the number of modes scales as k raised to d minus 1. But we know from our dispersion relation that omega scales as k raised to n, and therefore k scales as omega raised to 1 upon n, and therefore m of omega scales as omega raised to d minus 1 upon n. Alright. Now finally, in the last step, we'll note that omega scales with chi, and this result comes from the fact that chi is h bar omega upon kb t, and therefore finally m of chi scales as chi raised to d minus 1 upon n. So this is the scaling result we were looking for, and in this result the exponent d minus 1 upon n will hereafter be represented by alpha. So alpha is d minus 1 upon n. The usage of an online Mathematica CDF tool in which we'll plot the alpha moments of the normalized spectral conductance as a function of chi. Here chi is the normalized energy. It's denoted by h bar omega upon kbt. So what you see on your screen is the Mathematica CDF tool. It plots the normalized spectral conductance on the y-axis as a function of chi on the x-axis. For the ease of obtaining numerical values from these graphs, as well as for the ease of observation and trying to understand the physics behind what is happening here, I have plotted both the linear and the log scale graphs for the normalized spectral conductance. So this particular Mathematica CDF tool allows you to change the dimension of the system in question. So you can see the 3 buttons here. That's the 1 dimension, 2 dimension and the 3 dimension. And it also allows you to change the dispersion exponent with the use of a slider. So when the slider is towards the extreme left, that denotes the exponent as 1, which is analogous to the Debye sort of linear dispersion. And if I move the slider to the extreme right, that is more like a Za mode of graphene dispersion, parabolic dispersion. So I'm going to show a few specific cases to you and discuss the physics of the problem here. The first thing that you will notice here is that for a one-dimensional system or a device, there is no peaking in the normalized spectral conductance for any value of chi. And the reason for this is that the number of modes for a one-dimensional system is 1, and that is independent of the frequency and therefore chi. And because of that, all the modes contribute equally to the conductance, and therefore you see no peaking behavior. Now if I switch on towards a two-dimensional material by clicking on the 2D button, you will see the existence of a peak. So for a certain value of chi, the normalized spectral conductance peaks. Also, you'll observe that for a given dispersion, if I go on to a higher dimension from, let's say, the two-dimensional thing to the three-dimensional thing, the peak shifts to the right. Essentially, the frequency at which, or the value of chi at which the normalized spectral conductance peaks, it increases. The reason for that is because the density of states scales as omega raised to d minus 1, where d is the dimension of the system. So therefore more energy is contained in higher frequencies for higher dimensions. Therefore you will see that for higher dimensional materials, the peaking behavior is observed at higher frequencies. Once again, taking the example of a two-dimensional material, if I move the slider to the right, thereby increasing the exponent of the dispersion, the peak moves towards the left. And the same thing will be observed for a three-dimensional material. So I'll take the dispersion to be the linear case, and then I'll make it parabolic, and you will see that the peak is moving towards the left. This again stems from what we derived in the first part of the problem, wherein we showed that the number of mode scales as chi raised to d minus 1 upon n. So as the dimension of the system increases, the number of modes increase. On the other hand, as the exponent of the dispersion increases, the number of modes decrease, from that relation which we derived in the part 1 of the problem. And that is what you observe in the tool here. In the first and the second part of the fourth problem, we tried to understand how the normalized spectral conductance varies with frequency, and we even observed a peaking behavior wherein we saw that for certain frequencies the normalized spectral conductance reaches a maxima. In the second part of the problem, we observed that this peaking behavior is a function of the dimension of the system as well as the exponent of the dispersion relation. And we discussed an online CDF tool wherein you could actually plot the normalized spectral conductance as a function of chi, or the normalized frequency, for different dimensions and different exponents of the dispersion relation. So we are going to use the principles that we discussed in the first and the second part of the problem to apply, and we're going to apply these principles to a real material in the third problem. So the material in question for the third part of the fourth problem is graphene, and we are going to discuss the peaking behavior that is observed in different acoustic modes of graphene. Now we know that graphene has three acoustic modes: LA, TA and the ZA mode. The ZA mode is peculiar in the sense that it is more of a parabolic sort of a dispersion, whereas the LA and the TA modes are usually approximated under the Debye approximation. So talking about the LA mode is approximated with the Debye dispersion relation, and under this approximation we can write omega is Vg times k, where Vg is a group velocity, which for the LA mode is 21,300 meters per second. For the TA mode, which is again approximated via Debye approximation, the group velocity is 13,600 meters per second. While the ZA mode, which is more parabolic in nature, is expressed as omega is equals c multiplied by k the whole square, and the value of c here is 5 into 10 power minus 7 meters per second. So in the third part of the fourth problem, we are asked to find the wavelength which results in a maxima in the normalized spectral conductance, and we need to find this wavelength for the three modes LA, TA and ZA. We are also given that the temperature is 300 Kelvin. So we are going to use the principles derived in the first and the second part of the problem to get numerical values for the third part of the problem. Now, if you go back to your CDF tool, which we discussed in the second part of the problem, you will note that the normalized spectral conductance, which is given as the alpha moment of G prime chi, it achieves a maxima for a certain value of chi, and that chi I will write it as chi sub peak. So chi sub peak denotes the value of chi which results in a maxima in the alpha moment of the normalized spectral conductance. Okay. Now for graphene, we know it's a two-dimensional material and therefore D equals 2. For the LA and the TA mode, N equals 1, since this is a Debye sort of an approximation. And for the ZA mode, N equals 2, because it's more of a parabolic dispersion. So if you go back to your CDF tool and you input the values of D and N as these values respectively, you will find out that for LA and the TA mode, chi peak is given by 2.58, and for the parabolic dispersion, chi peak is 1.8. Right? So these values come from the CDF tool. Alright. Now we know chi is written as h bar omega upon kbt. Okay. So therefore for chi peak equals to 2.58, this results in omega equals 101.33 terahertz, and for chi peak equaling 1.8, the omega is 70.7 terahertz. So these values come from this relation, and of course we are given that temperature is 300 Kelvin. Alright, so now we have gotten the frequencies which result in a maxima in your normalized spectral conductance. So these are the frequencies. So 101.33 terahertz is the same for LA and the TA mode, whereas 70.7 terahertz, this is for the ZA mode. Okay. Now from frequency, we need to calculate the wavelength at which this peaking behavior takes place. So for the LA and the ZA mode, the dispersion relation is given as omega equals Vg times k, where the value of Vg for the LA mode is 21,300 meters per second, and the group velocity or Vg for the TA mode is 13,600 meters per second. And so if we incorporate these values of group velocity in this Debye sort of a linear dispersion relation for the LA and the TA, I'm sorry, this is TA, this is not ZA here. So if we use these values of group velocity in the linear dispersion for the LA and the TA modes, we can calculate the value of the wave vector, which will result in these frequencies which we calculated here, 101.3 terahertz. And we also know that wavelength is 2 pi upon the wave vector. Okay. So from these relations, we can find out that for the LA mode, lambda LA max is around 1.3 nanometers, whereas lambda TA max is around 0.84 nanometers. So reiterating this whole process, we found out the frequency for which the spectral conductance is maximum, and that frequency is the same for the LA and the TA mode. We know the group velocity for the LA and the TA mode, and if we substitute back into the dispersion relation, we can find out the wavelength at which this peaking in spectral conductance happens, and the value for that for the LA mode is 1.3 nanometers, and for the TA mode is 0.84 nanometers. Now if we talk about the ZA mode, the ZA mode is given by omega equals C multiplied by K square, where the value of C is 5 to 10 power minus 7 meters per second. We know the frequency for which we observe a peaking in the ZA mode, that's 70.7 terahertz. So we can find out the value of the wave vector and therefore the value of the wavelength, which will result in a peaking in the ZA mode. So I'll denote that wavelength as lambda ZA max, and that value comes out to be 0.53 nanometers. I will highlight the final results. And these are the values we were looking for in the third part of the fourth problem. Thank you.